Okay, so these are the two propellers of the Bicopter, just two, and it's only in the plane. Our model is going to be extremely simple here. It's going to assume, we're going to assume that there's a mass and inertia associated with the body of the quadcopter or bicopter. We need to know the length between the two propellers. There's gravity which it has to contend with. It's going to have the way this generates thrust or moves around is that you have the propellers create a force, and that force, as you can see in that figure, is always at right angles to the body of the propeller. So in this case, the propellers are mounted so that they're parallel to the body, so it's always going to be 90 degrees. So you cannot generate a sideways force. You can only generate a force in the direction right angles to the body of the quadcopter. Okay, let's define a few variables, and then we'll be all set to start this. So the position of the center of mass is described by x comma y, and then there's going to be an orientation associated with the bicopter. Okay, so everything I said, I'll put it down in words. So we have m and I are the mass, inertia, g and l are gravity and length as shown. U1, U2 are thrust forces. X, Y, phi are the degrees of freedom. Yeah, so here's the key thing which makes this a hard problem. In general, quadcopters are not trivial to control because of this. We have 2 actuators and 3 DOFs. So when you have less actuators compared to the number of degrees of freedom, it's an under-actuated system, just like the Pendelbird Acrobat, harder to control. So just like before, what we'll do here is we will basically write the equations of motion. Equations of motion, which is a precursor to doing anything. Okay, so remember I told you there are steps we'll follow for Euler-Lagrange. It turns out that first step is to get position velocity of the center of mass. Okay, so if it is multiple links, there's a lot of work to be done to find center of velocities or center of mass of multiple links, like a manipulator. In this case, it's just very trivial. It's x, y, phi are the positions. There's only one body, so it's kind of easy. Other velocities, so that's taken care of. Next, we'll write the kinetic and potential energy as a precursor to getting the Euler-Lagrange equations. So second step. Compute kinetic and potential energy. So the kinetic energy is T is half m v square. So velocity is basically x dot square plus y dot square, and I'm trying to write it in terms of the position velocity I wrote down earlier. And then it's also going to have energy associated with angular motion. So that's going to be half I omega square. So omega is phi dot. And then potential energy is mg y. Okay, so the Lagrangian is T minus V Okay, so we got that. If you want, we can write it down like this form: x dot square plus y dot square plus square minus mgy. Okay, the third step is to write the Euler-Lagrange equations. So what are the equations looks like? Well, it's d dt of dl dq dot minus dl dq. Here q is, let's say, j, qj is capital Qj. Okay, so here lowercase qj is going to be x, y, and phi. So we'll write three equations for the 3 degrees of freedom. Qj, the uppercase Qj, is going to be the forces, external forces in the x, y, and theta direction, so phi direction. Okay, so it turns out that this is the part which is going to take us a while to do. So we'll compute this. This is something which comes from the thrust forces. So we need to compute that before we can proceed with this equation. So the left-hand side actually is pretty straightforward. We already have the L. We just have to evaluate it. So not a problem. Let's try to compute uppercase Q J. Okay. Yeah, we'll get it in one shot by using something we've done before, using the Euler with using the Jacobian concept we've talked about before. So let's do that. Let's compute Qj. Yes, as I said, if this is our bicopter, let's put in an axis. This thing is going to tilt. Just assume that there's another axis like this, x1, y1. So we're going back to the homogeneous transformation in order to do this. Let's call this point as P, this point as Q, and remember that this distance we specified as L divided by 2. Okay. I've heard this. It's CME. It must be in civil engineering. So go. I'm trying to find who it is so I can drop it off. Can I drop it if you? Yeah, yeah. Thank you. Yeah, it's in the civil office. I can just drop it there. I appreciate that very much. No problem. Pranav, yeah. I'm Brett. Thank you. Nice to meet you. Yeah. I hope it's not a bomb. Okay. Okay, so Qj equals Jp transpose. So remember that there are thrust forces here, U1, U2. When I say thrust forces, they are basically forces which have units of newtons. I'm trying to convert those forces to Fx, Fy, and torque. So we'll use the Jacobian. So it's going to be Jp transpose times the force at P in frame 0, right? Everything in world frame, plus JQ transpose FQ in frame 0. We could use what we learned about Jacobians to compute Qj, uppercase Qj. We basically do Jacobian of the point P, where the thrust force acts, U1, times Jacobian of point Q, which is this point, where the other thrust force acts. So we will basically get that expression, and then that should basically help us solve for the equations of motion. So let's do that. So I wrote down the Jacobian as the rate of change of the position xp. This is uppercase X, which will have small and x and small y, which I'll talk about in just a bit. And then with respect to the degrees of freedom q. Okay, so let's get this. So I'll just write down here what I mean by xp. xp in frame 0 will basically store the x position of point P in frame 0 and the y position of point P in frame 0. And xq 0 will store the x position of the point Q in frame 0 and the y position of point Q frame 0. Maybe, if this is confusing, maybe I can just change this to R. Now it might be a little better because there is x is floating around. Okay, and what is Q? Q is basically the DOF. It's going to be x, y, and phi. So x, y, phi happen to be this is x, y, and then the phi is essentially this. Okay, so it's very easy to do this once we have computed RP and RQ. Okay, and then FP is actually also very easy. Let's write it down. Well, FP should be in frame 0. Okay, so that's going to take some time. Let's do that later. So everything boils down to figuring out RP and RQ. So let's do that. We'll do that with the homogeneous transformation we've learned in the past. So the homogeneous transformation is given by the following. So I'll just redraw this figure. X, Y, and then as always we do, we attach a frame which is not going to move well. Actually, this is not right. This frame is stuck to the floor on the ground somewhere. So let's draw it somewhere like this. And then the frame which is actually going to be attached to the bicopter and move is x1, y1, and this is O1. So what the transformation H10 gives you is essentially, if you remember, it's the rotation matrix. So write it down. This position of point 1, this point, with respect to frame 0, 0, and 1. Okay, what that is this is phi. Then the rotation matrix is a 2 cross 2 matrix given by cosine phi minus sine phi, sine phi, cosine phi, and then this 0 is 2 zeros. And this O10 is basically the position of point 1 in frame 0. So clearly that position is x comma y. And then this 1 is just a placeholder, which helps us to complete the multiplication later on. So now there are 2 points of interest. One point of interest is point P. It's at a distance of L divided by 2. And the other point of interest is Q, which is at a distance of L divided by 2 on the other side. Okay, so to compute the position of P in frame 0, the rule is H10 P1, P1 in frame 1. So H10 is whatever we have there, sine phi cosine phi 0, 0, x, y, 1. Okay, and then we need to put in P, the position of P in frame 1. Okay, so we've attached a local coordinate frame, x1, y1, and we need to know the position of P in that frame. So we can see that P is along the x1 axis. So its coordinate will be L divided by 2 for the x1, 0 for the y, there's no, it's sitting on the x-axis, and then there's a placeholder 1. Okay, so if we do this multiplication, we would end up with x plus L divided by 2 cosine phi, y minus y plus L divided by 2 sine phi, and then 1. And note that this is xp in the frame 0, yp in the frame 0 and 1. Right? We were after xp and yp, so we've got that. Similarly, q0 is h10 q1, which would be cosine phi minus sine phi sine phi cosine phi 0, 0, x, y, 1. Nothing changes there. Now the position of q in frame 1 is basically this point. So you can see that it is along the negative x-axis with the distance of minus L divided by 2. So minus L divided by 2, 0, 1. Okay, so again, do the matrix multiplication to get x minus L divided by 2 cosine phi, y minus L divided by 2 sine phi, and then 1 placeholder. Remember that this is going to give us x q0, y q0, and 1. Okay, so that's just the start. So we just got xq, yq, xp, yp. Now we need to compute the Jacobian. So if you go back and see this, we have the Jacobian as will be the Jacobian of this with respect to q and this with respect to q. So let's do that. Okay, so I'm going to write the definition of the Jacobian. So Jacobian of point P in frame 0 is going to be dxp0 dx dx p0 dy dx p0 d phi. Okay, similarly, dy p0 dx dy p0 dy dy p0 d phi. That's it. It should be a 2 cross 3 Jacobian. Okay, so remember that xp0 is x plus L divided by 2 cosine phi, and then yp0 is y plus L divided by 2 sine phi. Okay, so using both these facts, what the definition of Jp is and then value of xp, we can now start taking the derivative. So first, row 1, column 1, this one. So we take this expression and take its derivative with respect to x. That's going to be simply 1, right? Because it's just x. Okay, next we have dxp dy. So dxp with respect to y. There's nothing here which is as y, so this is 0. Okay, and finally we have dxp with respect to phi. So the first part is going to be 0 because it's x, and then second part we need to take the derivative of cosine phi with respect to phi. That will be minus sine phi. Okay, so you got the idea. So we just keep doing that for every single term here. So 0 again. So when you take the derivative of y with respect to x, this term, it's just 0, there's no x. you take this with respect to y, it's going to be 1, and then with respect to phi, it's going to be 0 plus L divided by 2. The derivative of sine phi with respect to phi is cosine phi. So that's Jp0. Okay, similarly, we can write Jq0 as dxq0 dxq0 dy dxq0 d phi, and then dyq0 dx dyq0 dy dyq0 d phi. Okay, where xq0 is x minus L divided by cosine phi, and then yq0 is y minus L divided by sine phi. Okay, so the same thing when done for jq would give 1, 0, derivative of this term with respect to phi is going to be, cosine is negative, so L divided by 2 sine phi. Then 0, 1, the derivative of this with respect to phi is going to be minus L divided by 2 cosine phi. Okay, so we've got Jp and Jq. Let's see where we are with respect to this. So we have evaluated Jp and Jq. We need to compute Fp and Fq. Let's do that. Okay, now we know something about the forces at P and Q. The force at P is basically the thrust force. Okay, so you see that, well, let me just take this figure, make it easier to explain. Okay, so what we notice here is that the force at P, okay, in frame 1, okay, the frame 1 is this, is clear. It's basically 0 for the x. There's no force in the x direction. There is a force in the y direction. It is u1. Okay, similarly, Fq in frame 1 is 0 and u2. What we need here is Fp in frame 0. That's in the world frame. The world frame was somewhere down. Actually, I shouldn't draw it here. That makes it confusing. So how do we find that? Well, we know there's a relation between frames. It's basically through the rotation matrix. So it's R10 Fp1. R10 is something we have already computed. It is here. This is R10 is this term. So we know R10, so we can write it there. So R10 is cosine phi minus sine phi, cosine phi. Fp1 is 0, u1, and this will be minus u1 sine phi, u1 cosine phi. Okay, and it won't be very surprising. You can find that without doing all this. It's just taking u1 and finding its component in the vertical direction. You can see the component in the vertical direction is going to be, let's see, this is u1. This is going to be the same angle as here, phi. So this is phi and this is phi. So you need to take the x component. This component would be u1 sine phi, but in the negative direction. So that's basically u1 sine phi negative direction. And then the vertical component is u1 cosine phi, because this is phi. So that is here. So that's what it comes. It's not magic. It's just that it just gives you a nice way of doing this. Fq in frame 0 would be R10 Fq in frame 1, the same equations. The same force, you'll get the same answer. And not very surprising, it's the same thing. Just the U's will change. Okay, so we are, I guess, almost there. Let me just make it slightly cleaner. Okay, I think we are all set to evaluate what we're really after, which is Qj. So Qj is Jp transpose Fp. We've completed all those things. So let's compute Q, uppercase Qj. Uppercase Qj is going to be the Jacobian, which I wrote down earlier. It is, okay, now it's going to be Jacobian transpose, I think, right? Jacobian transpose. And the Jacobian was here. It was a 2 by 3 matrix, so it'll be 3 cross 2 matrix. I need to take this, the transpose of this. So 1, 0, 0, 1, minus L divided space. So 1, 0, minus L to L divided by 2 sine of phi, 0, 1, L divided by 2 cosine of phi, minus U1 sine phi, U1 cosine of phi, plus same thing 1, 0, 0, 1, except that here it will be L divided by 2 sine of phi minus L divided by 2 cosine of phi. Okay, so after doing the math, that is taking the matrix product and summing it up, we get the following form. Qj is minus 1 U1 plus U2 sine of phi, U1 plus U2 cosine of phi, U1 minus U2 times 0.5 L. Okay, so what we have here is the force in the x direction, force in the y direction, and the torque in the phi direction. So those thrust forces, the propellers, are actually producing these forces. A force in the x, force in the y, torque in the phi direction. Okay, now that we have got Qj, what we were doing here, after all, is trying to compute this thing, this expression, right? And Qj was the one which was very time consuming, and we've taken some time to get that. But now it's just a matter of plugging in the values. So we've already have L is here. Let's just compute the equations of motion now that we have this. So here we are, equations of motion. I'll just write L, it'll help me to get the equations. Plus 0.5 I phi dot square minus mgy. And then Qj is, I'll write it as minus U1 plus, let me just not write this. Okay, so here are the equations, d dt, dl, dq dot minus dl dq equals Qj. Okay, let's start with Qj equals x. So d dt of this whole thing with respect to x dot. So you can see the only term which will be non-zero is this one. So the derivative of 0.5 m to x dot is going to be the derivative with respect to x dot. Okay, next dl dq. So dl dx, but there's nothing in here which is x, so this is 0, equals fx, but fx from the previous page was minus u1 plus u2 sine phi. Okay, so now we need to take the derivative of this thing with respect to time, and that gives us this 0.5 will cancel. So it will be mx double dot equals minus u1 plus u2 sine phi. Okay, so super simple, right? This is our first equation. Okay, next equation. Let's put qj equals y. So d dt of, so L is Q is Qj is y. So derivative of this whole thing with respect to y dot. So clearly the only term which will matter is this one. So it will be 0.5 m to y dot. Okay, and then dl dq. So dl dy. There's no y. There's only one y here. So derivative of that with respect to y is going to be minus mg. So minus mg equals the force in the y direction, which was Fy, which is this thing. So u1 plus u2 cosine of phi. So taking the derivative of this similar to that one will give us y double dot equals u1 plus u2 divided by m cosine of phi. This is 2. And finally, qj equals phi. So again, when we take the derivative with respect to q dot with respect to phi, to move this, I'm running out of space. Can eliminate this and move it up. Okay, so d dt of L with respect to phi dot. So the only term which will matter is this one. So 0.5 I to phi dot. And then dl d phi, there's no phi term here in L. So that's going to be 0, equals torque in the phi direction, which we computed in the previous page. It is u1 minus u2 0.5 L. Yeah. 2 phi dot because it's phi dot square. Derivative of phi dot square is with respect to phi. Okay, so then if we take the derivative, we get phi double dot equals u1 minus u2 0.5 L divided by I. So this is the third equation. Minus d. Thanks. Okay, so let's just simplify things by defining two new variables for the thrust forces. One would be us, let's call that u1 plus u2, and call ud as u1 minus u2. With that, what we can do here is we can define x double dot as minus us divided by m, and then phi dot is ud times 0.5. So we have x double dot equals us divided by m sine phi. Y double dot is us divided by m cosine of phi minus g, and then phi double dot equals 0.5 L divided by I UD. Okay, so that's what after. The thing to note here is that at 3 degrees of freedom, x, y, phi, and two controls. You could either count them as US, UD, or you could count them as U1, U2. Doesn't matter, but really two. There's no three. There's just a way of redefining the controls using US and UD. Okay, now let me tell you a little bit about the equations. I think this is kind of very interesting about drones. And when you see a drone, you might now be able to make sense of how the drone actually controls just by looking at this equation. So we have three equations: x double dot, y double dot, phi double dot. Okay, x is movement in the x direction, y is movement in the y direction, and phi is the angle. Okay, let's see what goes on if you. So here's some intuition. Okay, if you want the drone to hover, just float in the air. Okay, when the drone is hovering, what you'll see is it's in this configuration, right? And then I'll write down the equations here just for a reference. UD. No, 0.5 L divided by I. Cosine, sine. I did a mistake. This should be sine. This should be cosine. Okay, so first of all, if you want the drone to hover, when in hovering, phi is 0, right? If phi is 0, then x double dot equals minus u, I forgot minus g here. It's actually 0, right? So x double dot is 0 because phi is 0. Y double dot will be us divided by m. Cosine of 0 is 1 minus g. Okay, so if you want it to hover, then it's not flying up or down in the air. So y dot double dot should be 0. So us should be mg. That is, you need to put in a throttle inside in the two thrusters such that the sum equals mg, and then it'll be floating in the air. And then finally, phi double dot equals 0.5 L divided by I. You want to put UD 0, UD being the difference. If you put that equal to 0, that is U1 equals U2, then it will stay in that position. That is, if you do not put that equal to the U1 equal to U2, then phi double dot will not be equal to 0, which means that it will tilt. You won't want to tilt. So that's the hover position. Okay, now comes the interesting part. Let's just assume that phi is 90 degrees. Okay, what it means is that the drone is like this. Let's look at what the equations. We have for x, we have x double dot equals minus u divided by m. Sine phi, sine 90 is 1. Y double dot equals the cosine of 90 is 0 minus g. Right? Now look at this equation. In particular, look at this y equation. Y double dot is minus g, and there is no torque or there is no thrust force appearing in this equation, which means that once the quadcopter or bicopter hits the 90 degrees position, it's just going to fly down. There's nothing which you can do to control it. It's going to crash because there's no control here in this equation. So you never ever want the drone to be in this configuration because it's bad for the drone, it will fall. Okay, now the third is what happens if phi is between 0 and 90 degrees. So third one, if phi is between 0 and 90 degrees, what we're talking about is this drone is like this. The same configuration I drew it. This is phi is greater than 0. Okay, so if you look at the equations, in fact, let's just put phi is close to, I don't know, let's put a very small value, 0.1, okay? Very small value because it helps us to linearize the equations. So in this case, x double dot will be very similar to us divided by m. Sine phi is phi. Y double dot is similar to, so cosine of approximate 0 is 1. So this will be us divided by m minus g. And then phi double dot equals 0.5 L divided by I times UD. Okay, now if we wanted to hover, that is more or less we want US to be approximately equal to mg, right? If you don't have this, then what will happen is that the drone will basically crash down. So you want to have US is similar to mg. So we can rewrite this as minus, so US is my mg, so mm cancels off, so we have minus g phi. And then this will be mg, so mg m minus g equals 0. And then this will be something which is depends on the difference. But the interesting thing is happening here and here. So y double dot means 0 equals means stationary. Right? It's not going to go up or down. It's going to be stationary because the acceleration in the y direction is 0. But look at this term. It is minus g phi. Okay, so if phi is positive, which it is, minus g phi is going to be negative, which means that from this equation, x double dot will be negative. What does it mean to accelerate in the negative direction, with have an acceleration of negative? It means that this drone, which is going to actually it's going to move this way. So it'll go that way. Actually, it'll keep accelerating that way. It will not stop. You cannot stop it because of the condition. Okay, so the way you can stop it actually is this. Once it, so remember the phi is determining how much it's floating on the left side. But you can control phi in the following way. You can control phi double dot. So what you will do is the moment it goes to the left, you will add in some UD so that the tilt is back to 0. Once the tilt is back to 0, this is back to 0, x double dot will be 0, stop accelerating. So the way you control a drone is typically you will tilt it, you will go accelerate because of the first term, and then tilt it back using UD. And that's how you control a drone. You'll always see that the drone is doing this. It goes like this, balances, tilts, goes like that. So tilting is a way of making it go left and right. And then by making US be greater than mg or less than mg, you can go up or down. We can actually see this using a simulation. Uh, I've put the equations inside Python. Long code, but essentially we'll get to the crux of it, which is, okay, so here I'll start off by putting 0, 0, 0 for all the angles, velocities are 0. And what I'll do is I'll ensure that my control here is mg, right? US is mg, so it's supposed to hover. So if you run this, you'll see that it actually hovers. Nothing interesting going on because it's just going to sit there stationary. Okay, nothing, no interesting dynamics. Now let's do the interesting thing, which is let's change phi to 0.1. So the same thing I wrote down. So let's change this to 0.1. So now it's tilted slightly. As I said, if US is mg, it's tilted slightly, start moving to the left and see if that happens. So it's going to the left. I just keep going. I have not put a correction wrong. If you put the negative direction, if you look at the equations, it's actually accelerate in the other direction. So let's go here. So it goes the other direction. Okay, and then if you put 90 degrees, which you should not, it'll actually fail. You can't do anything about it. So np dot pi divided by 2. Yeah, it just goes crazy. So that's the intuition. Now, there's one more thing. I'm running out of time, which I wanted to show. I have to write the equations of this. Let me just, if you think we have time. Okay, the last thing I'll do before we switch is, how do you do tracking? If you saw the video, they showed how you can get the robot to track a curve, right? It went, let's say you want to track a circle or track some other curve. Let's see how to do that. So there's the feedback linearization, which we talked about. Feedback. I'm going to go about 2 minutes over time. So you can do feedback linearization for trajectory tracking. That is, let's say that you want to trace the curve weight, and that's the one I'll do. How do you get it to trace the curve weight? Well, this controller does that. X ref, Y ref is given. So assume that x dot y dot ref is given. And of course, x double dot ref, y double dot ref is also given. So the challenge here is that there are two controls, but there are three things they're trying to do. And that's where the challenge is. So you can actually write this controller very smartly. It's basically based on some intuition about the equations. So you make phi as a function of x, kpx, x ref minus x plus kpy. Oh. Okay, I'm almost done. Kdx, x dot ref minus x dot. So this is the phi reference. Then we have a control for US. There'll be mg plus delta US. So mg takes care of the hover part, but the delta US basically the feedback controller. It is going to be m y double dot ref plus kpy y ref minus y plus kdy y dot ref minus y dot. And then finally, we have ud will be delta ud. And this delta ud is minus kd phi dot minus kp. Let's call it kd phi, kp phi, phi ref minus phi. So this part basically controls the orientation to be 0. And we also need to track x ref, y ref. So that's ensured by these two equations. So this one is looking x ref. So here is what you get if you try to track it. So remember, it's also using the intuition behind the first thing, which is the first time I told you that it has to tilt a little bit in order to go there. It'll actually show up when I use this controller. So here is the final thing, which is this controller in action. So here we go. So figure 8, so it tilts, accelerates, tilts back, and the gains are manually tuned. So this is going to show a bunch of things: the thrust versus sum and difference, the plot of velocity versus time, position versus time. Tracking is good because the red follows the blue. Okay, so that's how you do tracking of a trajectory.